Hi, class. So this is our last lecture in chapter 21 on nuclear chemistry. And in the last chapter, in section 21.3, we talked about nuclear decay and writing some equations and also calculating half-lives. In this section, we're going to talk about transmutation and changing, that is changing from one element to another. Again, writing some nuclear equations and also identifying fission and fusion nuclear reactions. I wanted to point out in the last chapter, I talked a little bit about health effects. Well, if you read section 21.6, that's a nice read on the health effects of nuclear radiation, and it also includes how you measure that, which I touched on in the last lecture also. So let's go on to our last PowerPoint for this chapter. So I'll share my screen, and hopefully you can see it. So chapter 21.4, nuclear fission and fusion and transmutation. So one of the goals is to know what transmutation is. So be able to define that term. Be able to distinguish between nuclear fission and nuclear fusion. Be able to write a nuclear fission and nuclear fission equations, and not write it from scratch, but be able to complete those. So like we've written before, it's just basically completing a nuclear equation. So nuclear transmutation, that means when we've changed one isotope or one element, it's not an isotope, it's an element, when we change one element into another element. And that that's something that alchemists are always trying to do. Remember in the Middle Ages, the alchemists were trying to turn lead into gold, or gold into lead, or everything. They're trying to turn everything into gold. Well, the only way you can do that is through a nuclear transmutation reaction. And that's when that happens. So when one nucleus changes into another, when the number of protons changes, we've changed from one element into another element. That occurs when a radioactive decay happens sometimes. In fact, most of the time. So in the case of uranium-239, it changes into neptunium-239 and loss of a beta particle. Another occurrence is when a element, a nucleus of an atom, captures an incoming particle, high energy particle. In this case, it's a nitrogen-14, which is a stable element, capturing an alpha particle. So you bombard an element with high energy particles. They can be protons, alpha particles, beta particles. It can be another atom. And you get a new element. In this case, the nitrogen-14 becomes oxygen-17, and with release of a proton. The third way that can happen is through fusion, where you combine two elements through high energy collision, and you form a new element. So in this case, we have curium-246 being bombarded with carbon-12 atoms, or vice versa. And they fuse together to form nobelium-254 plus 4 neutrons are released. So this would be considered fusion, where you've taken two smaller elements and produced a heavier element. Fusion is a reaction that occurs in the sun, but that's between two lighter elements, between hydrogen and helium atoms. Okay, let's go on. So now we're going to talk about fusion and fission, and that's what worksheet 9 is about. So when we get to worksheet 9, we'll be looking at some of those equations. So fission occurs when a large nucleus is split into two smaller nuclei with the release of energy and radiation. And that there's an example of that on the previous slide, where I guess, yeah, I think uranium was split into two smaller elements. So here uranium is bombarded with a neutron particle, high energy neutron, and it splits the uranium into barium-141 and krypton-92 with release of 3 neutrons. So this is an example of fission, but it's not the only example. There are lots of fission reactions. This particular fission reaction is what occurs in a atomic bomb. That's what's shown there. So fusion occurs when two smaller nuclei combine to make a larger one. I've already stated that, with the release of energy and radiation. And an example of that is hydrogen 2 and hydrogen 3 being fused together to form helium with release of a neutron. So this is a non-radioactive helium. So I have a couple of examples of that. So when a nuclear bomb explodes, and also you have to have fissionable material, and U-235, there's lots of uranium, radioactive uranium isotopes, but the most common is uranium-238. But that you can't create a fissionable chain reaction. So in order for an atomic bomb to work, or to explode, or for a nuclear power plant to operate, you have to have a nuclear chain reaction where the energy continues to be produced. So uranium-235 is one of those types of radioisotopes. So when the high energy neutron hits it, it splits into two smaller nuclei, the release of 3 neutrons. And those 3 neutrons hit new uranium-235, so it's split into 2 smaller nuclei, which also release 3 on, and so forth, until you get this uncontrolled chain reaction, and that results in an atomic bomb. And the nuclear reactor, what they do is they'll put in rods to absorb some of these neutrons, so the reaction doesn't take off and run away out of control. So fusion. So this fusion, I have a short 3-minute lecture here, that kind of a video that explains fusion. So let's see. Let's watch that for a minute. I'll put this full screen so you can see it. Oops. We got an advertisement here. Let me see if I can skip the ad. Bye, Joe.
In this video, we're going to understand how 2 or more nucleons merge or fuse together to create something more powerful and meaningful. So let's start by talking about the word nuclear fusion. Nuclear means the process which involves a nucleus, and fusion in English means 2 or more entities coming together or merging together to form one single entity. So nuclear fusion can simply be defined as the fusion or combination of nuclei. Scientifically, nuclear fusion can be defined as a nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amounts of energy. For example, lighter nuclei such as lithium and helium when combined together, form a heavier nucleus. The mass of the heavier nucleus is less than the initial reacting nucleus. The word heavier here is phrased in terms of energy release, which is usually very enormous rather than mass. Therefore, the law of conservation of energy is satisfied. Consider the example of two hydrogen nuclei combining to form deuterium. Here, one hydrogen atom combines with another hydrogen atom, giving deuterium, one positron and one neutrino. This deuterium, in turn, combines with another hydrogen nucleus to form a helium isotope. If two such helium isotopes are fused together, formation of heavier helium takes place. These three steps of a nuclear process, where 4 protons are fused together to form the heavier helium-4 nucleus and enormous amount of energy, is a nuclear fusion reaction. The chemical equation for this nuclear fusion is as follows. 4 hydrogen nuclei, when fused together, give rise to the heavier helium. But how is this enormous amount of energy being liberated from such a seemingly simple nuclear reaction? To understand this, let's first calculate the loss of mass in the process. The starting mass of the 4 protons is 4 times 1.0078, which is equal to 4.0312 AMU. But the final mass of the helium nucleus is 4.001506 AMU. Therefore, the loss of mass is 4.0312 minus 4.001506, which is equal to 0.0297 AMU. This is equivalent to the energy given by Q is equal to 0.0297 AMU times 900 mega electron volts per AMU, which is equal to 27.67 mega electron volts. Wow, that is a significant energy release coming from the fusion of the 4 protons. However, in spite of such a substantial amount of energy being released from the nuclear fusion reaction, there are no full-time nuclear reactors built so far for fusion reactions, as it is very hard to control such enormous energy release.
You are going to laugh at the old you by the time.
All right, let's get out of this. Whew, okay, so that was a fusion video. So let's look at an explanation of fusion. So let me get back. Okay, I'm going to stop my screen share. And I want to look at this worksheet. So if you can't see the worksheet, go to your gallery view on your screen. I think gallery or participants, and open up the notepad, or say spotlight the video of the notepad, and you can see it. So the first page of the worksheet 9, as you open it up, is an explanation of fission and fusion. And in the fusion reaction, they show an example of hydrogen 2, which is deuterium, and hydrogen 3, which is tritium fusing and forming a helium atom, helium-4 plus 1 neutron. So as in that video, there are lots of reactions that can occur between the different hydrogen isotopes to produce different helium isotopes. And there are a few of these shown below, a few fusion reactions. So let's look at the worksheet now. The worksheet is basically just completing some of these reactions. So in the first reaction, it says as an equation in the model shows the fusion reaction of 2 deuterium nuclei, which are hydrogen 2, to form a nucleus of tritium, which is hydrogen 3. Suggest another product that might form in this reaction. Well, another product that I've seen is helium 3. So if we write helium-3, here's helium-3. Helium has 2 protons, and helium-3 means it only has 1 neutron. Excuse me, that didn't come out that great. That's supposed to be helium-3. Plus, we need to balance this. We would balance it with a neutron, with 1 neutron. Okay, so that's one reaction. You know, you might make a helium-4 plus a gamma ray, perhaps. So usually have energy released in some form of radiation. If we formed helium-4, then we have the right number of protons and the mass. And the radiation that would be released would be gamma, because gamma has 0 mass. In that video, they talked about neutrinos. Well, neutrinos are what I call mini subatomic particles. So we didn't talk about neutrinos, but there are lots of, I think they're known, physicists are discovering new subatomic particles all the time. There are many of those. If you're interested, you can look up, you know, what are all the subatomic particles that are known. But as chemists studying chemistry, we're just primarily interested in protons, neutrons, and electrons. The second question is, describe how to find the identity of the species X in this equation. Well, you don't have to explain it, but I'd like you to fill in species X. So in this case, we have uranium-235 plus a neutron is yielding a Nd might be neodymium. I'm not sure what Nd is, but it's 152 and a different isotope, so it's splitting. So this would be an example of a fission reaction and 3 neutrons. Let me look previously at that. There's a different uranium fission reaction over here. Okay. I think I see the one that we're looking at. It's over here on the front page. So some of these you can find on the front page. It's right there. Okay, so let's go back. I'll let you complete that one. What is missing in the following reaction? So again, this is a fission reaction. I'll let you fill that one in too. Let you do those two. That might be another one that you can find on the front page. Let's go to question 4. An atom of U-235 absorbs a neutron and produces an atom of antimony-125 and 4 neutrons. Identify the other nuclide formed in this reaction. Write the equation to support your answer. So you can write, I'll write this one out. 235, U-235, uranium is 92. It absorbs a neutron, so I'm going to put a neutron here, and it's going to produce an antimony 125. And again, you're going to need your periodic table to get the atomic numbers for these. And where's my, I don't have my periodic table right here. So I might have to do a little searching. So let's add our new, and create some boxes here. Plus, says this produces 4 neutrons, 4 neutrons. So we can see that we go from 235 to 125, so that's a loss of 110. But we have 4 neutrons here with a mass of 4. So that means we need to put a 106 in here. 106. So 106 plus 4 plus 125. See, 106 plus 4 is 110. 110 and 125 is 135. So that's okay. And then we're going to have to look up a the atomic number of antimony. So let me get my periodic table. So, let me get back there. Sorry. Okay, I'm back now. So antimony is 51. We put a 51 here. And so we've gone from 92 to 51. Take 92 minus 51 and we get 41. And if you look up element 41, 41 is, I think it's niobium. And so that's it. Question 4. So question 5 doesn't have any balancing, but it wants you to identify these as fusion or fission. And so fusion, remember, is smaller nuclei becoming a heavier nuclei. So that happens here. So we've got 2 smaller nuclei becoming 1 heavier nuclei. So I'd identify this as fusion. In the second case, we have a heavier nuclei, U-235, being split by a neutron into 2 smaller nuclei. So we have fission, and I'll let you finish the other 2 equations. So that pretty much finishes our lecture and worksheet on section 12.4, and also finishes up, excuse me, section 21.4, not 12.4, and finishes up chapter 21 of nuclear chemistry. So that's all for now, and I'll be back later. We're going to start chapter 13 next, which is a completely different topic. So goodbye for now.